All right, hopefully you've tried the example problem before I do it. If you have not tried it, you need to try it now. No option, sorry. Try it. You should be able to do this without me teaching something new. I'm going to talk about some new things, so I want you to be able to do it without the new. Does that make sense? So try it out. If you can't do it, meet me here. If you can do it, follow along with what's different and new. Either way, if you haven't done it yet, pause and unpause. So here we are. We'll look at this problem. It is, what do we call these? Volumes of revolution. So what we're doing is we're picturing an object like a line. We're picturing a line like so. Here's my graph of my line. And we're saying this line right here, we're going to spin it around the x-axis. We're going to spin it this way around the x-axis. When I do that, this piece here comes all the way over to here. And then I end up with a cone, right? And so if I spin it like that, we call this a problem of revolution. Okay, so we're taking a function and we're revolving it around the x-axis. Okay, and that's basically what it's boiling down to, and that's what a revolution problem is. Now, the good news is we've already done this sort of problem. We just did it in a totally different context. And so the deal is, what's the shapes I'm walking through? Well, if I'm starting at the origin and I'm walking this way, let's say, I'm walking through, what's the shape? Circles, right? I know the area of a circle formula, so I'm walking through circles. What is the radius of these circles? The radius of this circle, it varies. It's different. Oh, bummer. So then I'm going to say, well, the radius of the circle is going to be y. Agreed? It's how high it is in the y direction, though, right? For every place along the way, initially before, the end it's 0. Everywhere it's just the height of this y function, of this line that I'm drawing. Okay? What's a volume? So now I go ahead and do, all right, so here's what are we going to do? We're going to then do, pen's not working. Okay, so then I'm going to go, how do I find out what the volume of it is? Well, we do what we did before. Nothing's changed here. We go, what's the area formula? The area formula is pi r squared. So in this case, my area formula is going to be pi y squared. I don't like y because I'm walking in the x direction, so I need to write y in terms of x. So I look at this little line up there, and I go, that's a line. How to write an equation for a line? Y equals mx plus b. If this is my origin, which I'm going to set it to be to make my life better, then I would say y equals, what's my slope? I'm going down 4 over 8, so that'd be negative 4 over 8, which is going to be negative 1/2 in a second. X plus, what's my y-intercept? My y-intercept would be 4. So I'm going to put a 4 there. And so my equation for y is, in terms of x, is equal to negative 1/2 x plus 4. Now that I have that, I can write that my area formula is going to be equal to pi. This should have been a pi. I don't know what happened there. That's very bad. Times negative 1/2 x plus 4, that whole thing squared. So how do I find using my old volume formula that we've been just dealing with? We're going to integrate this thing, right? We're going to say the volume is equal to the integral starting at 0 and ending at, we're walking the x direction, so we're going to end at 8 of pi times, now I'm going to mess this thing up. I'm going to look at this and go, ooh, this is really icky, but I'm going to go ahead and FOIL this up, and I get 1/4 x squared plus, not plus, it's going to be a minus 4x plus 16, right? And so that's going to be dx. And so I want to find, so I'm going to have to integrate this to find my answer, and I'm going to go v equals, I'm going to pull my pi out because I don't want it inside of there because it's icky. I'm going to clean this thing up, so I'm ready to go. 1/4 x squared minus 4x plus 16 dx. Integration time, v equals pi. This becomes, raises power by 1, divided by the power I get, 1/12 x to the third minus, this should have been 0 to 8. I don't know what happened there along the way. Got it. Okay. Minus x squared plus 16x from 0 to 8. This looks like a great time to use a calculator, although you really don't need a calculator for this one. I'm going to anyways. 8 up caret 3 divided by 12 minus 64 plus 16 times 8 is Boom, 106 2/3 times pi. Where's my pen? There's my pen. So volume is equal to 106 2/3 pi, whatever the units would be, cubed. All right, so that's how we're going to find the volume of something that's being rotated around the axis. Now, that's nice, and it works, and it's exactly what we've been doing all along. There's nothing wrong with approaching it that way. But if you do enough of these problems, you get pretty bored of the same routine over and over again. So might I suggest to you the following. What this is this is the radius, right? Right? And so if I can write, what I'm going to do here is I'm going to say, look, the volume of something rotated around the x-axis is going to be the integral from 0 to the final value of, actually from a starting point, because it could be something other than 0, to the final point, right, wherever I slide along the x-axis. I'm going to have a dx. I'm going to put a pi out in front. Y could always be a constant. So it means I can always pull it out. Pi r squared. What's r squared? I'm going to write r in terms of x squared. And so this formula is a quick way to get to the fundamental answer. So you can just go ahead and just jump right to this and not bother with all this hanky stuff that you've been dealing with before. So if you have a function, you just write the function in there and you're good to go. Whatever the function you're rotating becomes this equation right here. Now, what if you're going around the y-axis? Well, just change all the x's to y's and use exact same formula, right? All right, so here's what you're going to do. You're going to try problem number, I don't know what it is, so I'm going to look quickly. Problem number 1. Try problem number 1, and when you get done with problem number 1, this one right here, we'll have a conversation about how we did on that. If we got that, then we should be in really good shape, okay? So try problem number 1, and then we'll do problem number 1, and then we'll see if you've got it. All right, so using our new idea, we simply go, V is equal to pi integral. It's rotating around the x-axis, so therefore I'm walking along the x-axis through my circles. So it's going to be from 0 to, where does my shape end? It ends at 1, so I'm starting at 0, ending at 1. What's my radius equation? My radius equation is negative x plus 1 squared dx. And so now I'm going to roll on through here as fast as I possibly can go. Pi equals, I'm going to change this out to become x squared minus 2x plus 1 dx. So now I'm going to go V equals pi times x to the third over 3 minus x squared plus, I dropped my 1 here, that's not great, x from 0 to 1. I plug in my 1 and I get pi 1/3 minus 1 plus 1. That is the world's worst pi. Actually, I had worse one on the previous page, so I guess that isn't the world's worst pi, but it's pretty close. And then when I do a little bit of work, I get 1/3 pi, and that's the answer to the question. By the way, this is how we know the volume of a cone formula, which you've theoretically memorized someplace in 6th grade, which I honestly think was a waste of time when you did it. But in any event, this is the area of the volume of that cone. All right. So I'll blow through the rest of these. They should be fairly straightforward. You just simply plunk it in the formula and call it a day. Remember, if you're rotating on the y-axis, you're just going to change everything in terms of y. Your formula needs to be in terms of y as well. Okay. All right. And then your starting point, any point, it can be in terms of y, right? That's all that changes. Okay. All right. See you on the other side.